absolute valued that, let's just say consider this guy. Just that guy, just the positive stuff. Can we compare that with what we've talked about so far in this class? Well, I feel like this is class, it's not class. We're supposed to be having fun here. So, what can you tell me about that denominator? James, help me out. I want to compare this. Doesn't that feel like 1 over 2 to the n? Which we feel like should be convergent? So what would I have to put here to make that happen? Make the denominator smaller, it'll make the fraction bigger. If I make the denominator bigger, it'll make the fraction smaller. Right? Is that the way I want? Or I want the other way around? The other way around. Make the denominator smaller, makes the fraction bigger. That's what I want, right? And what is that? Geometric. In fact, it's exactly, which is a ratio of less than 1 and hence instantly convergent. So doesn't that prove this is convergent by comparison?
Yes.
Assuming we've talked about the positive stuff, which is positive because I absolutely value the damn thing, right? So it's convergent. This guy is officially convergent by comparison because the absolute value is convergent, so is the original. In fact, we call that absolutely convergent, right? So here's an example that doesn't really help reinforce what I've said as a problem because the limit went to 0, didn't it? Which means most students go, oh, instantly convergent. And they'd actually be right in this case, but I'd still take points away because they didn't check decreasing, right? In fact, if they did, it would be wrong. So it's convergent, but not because of the alternating series test. It's convergent because of a comparison. Now let's take a look at this guy over here. Now this is where I want to bring him back, if you don't mind. Remember this guy? I want to bring him, and I want to bring one more guy to the party. I think we already saw him, though. So let me write this guy down. It's 1 over n plus negative 1 to the n root n. I want to bring him together. And there was a really quick alternating series that we did. It was this guy, right? That was my very first alternating series example. Yes, sir, question?
Would you need a less than or equals inequality?
You're right. It is actually less than or equals. For certain ends, they'll be exactly the same. Thank you. But let's talk. This guy was divergent, right? And what was this guy as a series? It was convergent. So what happens when you add or subtract a convergent and a divergent? It's divergent. Wait for it. Wait for it. Common denominator, right? So common denominator here would be root n minus this guy times that guy, which is what? Negative 1 to the n times n plus negative 1 to the n root n. Right? All over common denominator. So what happens in the numerator when I distribute this to both of those guys? Well, I got my root n, and then negative 1 to the n times an n is, well, it's just going to be negative 1 to the n times n. And then what happens right here? Negative 1 to the n times another negative 1 to the n is always positive, right?
Yeah.
So we get minus root n, because it's a negative being distributed, all over common denominator. And of course, what do you see upstairs? Get the happy hiya marker out. Hiya, hiya. And well, one final little step. What do you say we factor out a square root of n here to go with that other square root of n? That's going to give me an n out front. And what's left is the square root of n plus negative 1 to the n. And upstairs it is negative 1 to the n times n. Wait for it. Hiya, hiya. which gives me the opposite of actually what I've got, so I should have subtracted the other friggin' way. But what I'm looking at is, isn't that my series in question? Times -1, but subtract the other way, you get rid of that problem. What does that mean about this thing as a series? Why? Because I said it earlier. No, because it's the sum or difference of a divergent and a convergent, which means it must be divergent. We proved that. That statement, which is almost a homework problem or pushed away to the backside of the textbook or not made to be a big deal, has been useful now 2 or 3 times during this little talk with basic examples that now shows, well, you can't just do the limit as n goes to infinity and say convergent, because here's an example that is divergent, and then right after it another one that is convergent, which hopefully will then clear up that misconception and avoid you all from just saying, oh, the limit went to 0, it's immediately convergent. Correct? Okay. So those were the really tough ones, right? These examples, I have to mention that something Professor Johnson told me. These examples are not like, oh, well, obviously, this is, everybody thinks of this. No, this took a lot of blood, sweat, tears, toil, frustration, trying to come up with really nice examples that would make a lecture clear and also avoid any potential misconceptions that I have actually fostered in the past. When I've taught the class and I've said, oh, it's convergent by the integral test. You liar. It's not. There's an integral test and there's a test for divergence in there. So that's what makes these kind of fun. I have other ones, but we're going to get short on time. So what I'd like to do, if you don't mind, is very quickly show you the alternating or the ratio test example. So here's a ratio test, which again, I'm assuming you've heard of the test before. You do a limit of n plus 1 over n, and then you see what you get. If it's less than 1, it's convergent. Greater than 1, it's divergent. Equal to 1, go do more frickin' work. And so the example for this guy, the reason it's so tricky is this unusual product expression. Right? That's what typically makes this thing hard, right? Special or different than the common examples, should I say. Because when you discuss that, is that a factorial? Is 1 times 4 times 7 ... stop at 3n? Is that a factorial?
No.
It ain't. So we have a problem, right? But we can still do it. So let's take a look at the ratio. Lim, n's running off to infinity. A sub n plus 1 is basically put n plus 1 in there for all those guys. So 1 times 4 times 7 ... times 3 times n plus 1 minus 2 all over 2 times n plus 1 factorial, right? And then you divide it by the a sub n guy, which I'll just multiply by the reciprocal to save some time. So 2n factorial. And then this is n factorial times 1 times 4 times 7 ... 3n minus 2. Right? And you get your little hiya marker out and start canceling the hell out of stuff, right? So what is this guy? Usually the factorials end up working really, really nice. When I cancel those two, what are you left with? N plus 1. In fact, the clever way to do it is to write it out as n plus 1 times n factorial to show the canceling, and then you can go hiya, hiya, right? Well, we're going to use that same trick for all of this. What does this look like? 2n plus 2 factorial, right? Which I want to cancel it with 2n factorial. So how many terms more are there in this product than there are there? 2 more. So you write them out to show the instructor instead of just guessing. 2n plus 2 is the first one. The next one would be 2n plus 1. And then you keep going all the way down, so I'm just going to write that as 2n factorial. And you can go, hiya, hiya. Right? So that trick worked great for both of those, and, well, the same trick works for these guys, right? So what is this, if I were to write it out? 1 times 4 times 7, what's the last term there? 3n, and then it's plus 3 minus 2, so plus 1. And what is this guy's last term? 3n minus 2? But how are those related? Like the factorial, it was obvious because they go in order. All of them are there. What's the difference between stopping at 3n minus 2 and stopping at 3n plus 1 in this weird, funky product? How far are they jumping each term? By 3? So what's the next term after 3n minus 2? If I added 3 to that, wouldn't it be
3n plus
So, in reality, what's right here is 3n minus 2, isn't it? And so all of this will cancel with all of that, leaving me 3n plus 1. So let's write down what's left, because that's sloppy as hell. And if this was me grading, I'd be like, I can't read your work, show steps, minus 1. No, I wouldn't have fun. But let's see what it turns out to. Tell me what's left. I got an n plus 1 right there. I got a 3n plus 1 there. And downstairs was just those two guys? So 2n plus 2 and a 2n plus 1. So what's that going to turn out to? Just real quick argument.
Squared over n squared.
Top is an n squared. Bottom is an n squared. Algebra says degrees are the same. Take the ratio of the leading coefficients. Or do L'Hopital's rule. Or divide up by the highest power. I don't freaking care. It's math 31 at this point. Do the damn limit. What do you get? 3/4. Done. It's less than 1. It's convergent. Right? So the only thing that makes this tough is that canceling game, which you have to be extremely careful because it is not a factorial. It is a funky product. So I'm going to leave you now with the last slide, if you don't mind. Write these down. Because I don't know. And this was a slide that's up here due to Ken Johnson. Is he wanted me to be clear with you all that even though these examples are really nice, this is the stuff that I slugged through, and I still don't know the answers. Every test I've applied to these doesn't help. I get inconclusive, or the test is invalid. And so I'm not sure what happens to all of it. I have a feeling, like, this guy's a really interesting one. What's so interesting about this? Is that an alternating series? No, it sure ain't, because it's plus plus minus minus. So that's an interesting one in and of itself. But I think I can do this one with a ratio, right? If you do everything absolute value-wise, it turns into a geometric. So I'm pretty comfortable with this guy. But this one, and this one, and this one are all ones that I was trying to produce as an alternating series, as a good example for class. And all three of them, I don't know. The answer is Chuck doesn't know. I have no freaking clue. And this guy right here, talk about getting pissed off at this one. It's basically this guy right here, right? But what happens? I put in this 4/3 in there.
Should there be a parenthesis around the 3n minus 2?
3n minus 2. Yes, actually there should.
Okay.
That's a typo. Sorry. I didn't care about that one though because I couldn't do it. So. No, it's frustrating, of course, when that happens. But yes, that should be in a parentheses. And well, it's basically this guy right here. But what's going to happen? Because of the ratio test, you're going to put a 4/3 in here, which is going to cancel that 3/4, and you get freaking 1. Which means, I don't know. Yes, sir?
The bottom right view, it's not alternating because it goes plus plus minus plus plus or something. Many times you can redefine it to regroup those so that they are the result is alternating.
So that's what I'll end with, is these examples frustrated me and I couldn't do it. But there's a whole nother talk that I would like to do at some point on rearranging series. Because as we were told at the very beginning by Professor Abel back in 1826, divergent series are the devil. And if you rearrange something that is divergent, you can get into some serious hot water. So rearranging series may be okay given certain conditions. In fact, what I'll leave you with for your own benefit, besides trying to answer problems that Chuck couldn't do, which if you tell me, you must tell me if you get them, because I'm done working on these. If it's a absolutely convergent series and you rearrange the terms, however you'd like to rearrange them, the sum will still be the same. And it is still obviously convergent. If you have a conditionally convergent series and you decide to rearrange the terms, it'll still be convergent, but you can now make it add up to whatever you want. That's a proof. There's a proof that says the rearrangement of a conditionally convergent series can be summed up to equal k, where k is whatever you want. So rearranging series, and of course if it's divergent, then you're in real big trouble. You have no idea what you got there. So be careful with rearrangements, but it is a very fun talk. Maybe we'll save that for next time, okay? So thank you guys all for coming. Eat snacks on the way out, and if you have any questions, I will hang out until I have class at 11, so...
And if you want more fun, the math contest is at 2 o'clock in Weaver 110.
Oh, yes, that's right.
Read a yellow flyer.
So I will hang out and answer questions if you have any, or